All right. I think we're good. I will begin. Dearly Father, we thank you for this day. We thank you for the flood not being worse here, and help people who are still digging stuff out of mud and whatever. You'd help them to repair and rebuild their lives. We just pray that you'd bless this class today, Lord, and just help us to understand the material together, Lord. In your name I pray. Amen. All right, so first things first. Let me write the definition of uniform convergence for us again. And here it is. Let Fn be a sequence of functions. All right. On E, which is, by the way, some subset of the complex number system. All right. And suppose Fn converges uniformly to F, which is a function from E to the complex numbers again. We say this is a weirdly worded definition at the moment. We say this when, for each epsilon greater than 0, so I'm defining uniform convergence right now, okay? For each epsilon greater than 0, there exists n, big N, in the natural numbers such that n greater than or equal to n implies the absolute value, or the modulus if you like, Fn of x minus f of x is less than epsilon for all x in E. So this little extra condition here for all x in E means that this one choice of n has to work for all points in the domain, right? And that's the distinction. Like pointwise convergence would mean for a fixed x, we can find an n such that we can make that Fn of x minus f of x less than epsilon, right? But if you can find one n that does it for all the x in the domain, then the sequence of functions is said to converge uniformly. Now, courtesy of Gamelin, there's a nice way to think about this. We can talk about, we can get uniform convergence if there exists a worst case, he calls it the worst case estimator, which he says epsilon sub j. And what he wants for this epsilon sub j, he wants to have that fj of x minus f of x, all right, is less than or equal to epsilon j. And what else? He wants that epsilon j goes to what? Goes to 0 as what? J goes to infinity, right? If you can find such a bounding thing, this epsilon sub j, this worst case estimator, then that would suffice to prove uniform convergence. All right? There's a little theorem there that you could prove, but we're going to assume that theorem, all right? So for us, another way to capture uniform convergence is if we could find a worst case estimator, this bound on the difference of Fn, fjx minus fx, then, and so a good candidate for the worst case estimator is the supremum. So we'll take epsilon sub j to be the supremum sup of x in E, looking at fj of x minus f of x. So this would be the least upper bound of those values, all right? Least upper bound for the set, you know, fj of x minus f of x modulus such that, you know, j, well, excuse me, such that x is an e. Right, that's a set of real numbers, and so we can talk about its least upper bound. If that bound is attained, then this is just the maximum, right? All right, so what I'm trying to say is to check on the uniform convergence of a sequence of functions, all we really need to do is to calculate the supremum. If it exists and we can show that it goes to 0 as j goes to infinity, then we're in business. All right? So let's actually calculate the supremum for a few things, because it's a new idea for you guys, I think. Yeah? So number one, let's look at fn of x equals to x to the n. And I'm going to keep these real if you don't mind. I mean, I made the definition for complex because that's what we're really interested in, but my examples will be real. You'll forgive me. These are also the ones we looked at the graph of last time. All right, so I'm just adding some detail to what I talked about on the projector. So this one here, what would be the supremum of x to the n minus f of x? And so you know, 0 less than or equal to x, less than or equal to 1, right? And here, we'd argued what? We saw fn of x goes to f of x, what? What was that? It was 0 for x less than or equal to, oh, excuse me, for 0 less than or equal to x less than 1, and it was 1 if x is equal to 1, right? That was the limiting function as n goes to infinity. So what's the supremum of this difference here? As you take values from 0 to 1 and you think about that expression, what's the least upper bound on that difference? What's the biggest difference you could have there? Let's see, if we plug in like 0.999, right? X to the 0.999 is kind of close to 0.999 for n, for finite n, right? Oh, n is fixed here for the moment, right? We need to think about n being fixed for this calculation. That's going to give us something. Then after we're done with that, we think about n going to infinity, okay? One thing at a time. So n is fixed for this calculation. I could put x to the j here just to be more in tune with my worst case estimator comment, yeah? Yeah.
We can choose an x close enough to 1 such that the difference there is as close to 1 as possible, since if you know that side is 1.
Right. Exactly. So if we think about this for a second, you can see that you can produce values arbitrarily close to 1, because f of x, if we take x less than 1 itself, is 0. But the x to the j goes to 1 as we're getting closer. Yeah, so anyway, long story short, think about it for a little bit. 1. Yeah. Now, think about this. If this is a worst case estimator, if epsilon j is a worst case estimator, let me say, if this is another worst case estimator, let's say epsilon j tilde, where does this epsilon j have to fit with regard to this inequality? Like, this is the least upper bound, right? This is, epsilon j tilde would serve as an upper bound. So if this is the least upper bound, that means that you got to be able to pigeonhole epsilon j in there, right? I mean, you got to have less than or equal to epsilon j, less than or equal to epsilon j tilde. Yeah. In other words, if the worst case estimator is not the least upper, if it's not the supremum one, right, it's got to be above the supremum one, right? And so if the supremum, if the worst case estimator constructed with the supremum of the difference fails, any other one will fail. So I say that this, I'll just put it in red, this is the best worst case estimator, right? This is, if this works, it works. If this doesn't work, well, you're out of luck. And we just saw that the best worst case estimator, this one, right, is equal to 1, right? This does not go to 0 as j goes to infinity, right? Therefore, you know, this sequence of functions, f to the n, fn is not uniformly convergent to f on 0, 1. Yep.
So when you're calculating that as 1, is it okay if you said like x could be 0, so then 0 to the j is 0, and then f of x could be 1, and so now...
F of x is only 1 at 1, though. You have to think about the same x.
Oh, okay.
We can't think about different x in different, like the formula is for x. So if we put in 1, we get 1 to the j minus 1, which is 1 minus 1, which is 0. So it's not the endpoint that's doing for us, it's that getting close to the endpoint. It's exactly where there's that rip, as we contrast the limit function from the finite functions, there's that like discontinuity point. It's that. Right, that is not the maximum in this case. Yeah, there is no maximum to the set. All right, let's see here. I'll jump ahead to fn of x equal to x to the n over n. So if I look at the supremum, again, 0 less than or equal to x less than or equal to 1 for this one. And what do we say this went to what as n went to infinity? This just goes to f of x equals to 0, right? As n goes to infinity, you go to 1 over n, which still goes to 0. So the limiting function removes the discontinuity by dividing by n. So the limit function there, as n goes to infinity, point-wise convergent to this for sure. So the supremum of x to the n over n minus f of x, yeah? Well, that's just 0, right? I mean, so what's the supremum? Now that's what's the largest x to the n over n attains from 0 to 1. This is easier to think about. I mean, I can actually prove this one in a way that I don't mind doing. We've got 0 less than x less than 1, right? So 0 is less than x to the n is less than 1 to the n, which is 1. So 0 is less than x to the n over n is less than or equal to 1 over n. So as n goes to infinity, oh, so you see that, I think you can see that this is actually equal to 1 over n. That's definitely an upper bound for x to the n over n. And you could prove by contradiction that that's the best one.
So here the supremum is the maximum?
Here the supremum is the maximum, yeah. And, although I have forgotten that I was going to do it for j, so change of variables here, epsilon sub j is 1 over j, just to stick with my stupid nomenclature. And you can see that this sequence of functions is uniformly convergent, because as j goes to infinity, 1 over j goes to 0, right? So therefore, this goes to 0 as j goes to infinity. X to the n over n converges uniformly to the 0 function on the unit interval. This was the example we observed that we could interchange the limits, right? This was an example where we showed that we had the limit as x approaches 1 from the left, limit as n goes to infinity, and that for x to the n over n was equal to the limit as n goes to infinity of the limit as x goes to 1 from the left of x to the n over n. So this was the this was the one where we were able to switch the limits, and also where the limiting function for the sequence of functions was continuous, just as every function in the sequence was continuous, right? So we maintained continuity to the limit function here as well. All right, so why does what? As n goes to infinity, because as n goes to infinity, before what?
Why is f of x equals 0?
That's the limit. As n goes to infinity, it goes to this. I mean, the reason I'm pointing at this is that supports that claim. So as n goes to infinity, you can see that this formula is bounded by that. And that goes to 0 for arbitrary x between 0 and 1, which says that's the limiting function is the 0 function. All right, so so this is, just a couple of actual, on-the-ground calculations for you about how to show uniform convergence for these specific examples. And as I mentioned, there's a theorem that theorem 10.3.8 says that, if we have f, I use J now, okay, a sequence of complex valued functions on E, which is some subset of the complexes, and then if each fj is continuous on E, and if the convergence of the sequence, if this converges uniformly to f on E, then punchline, f is continuous on E. So example 2 is a particular case of this theorem. Because continuity of the limit function basically means that you can switch the limits, right? That's part of it, but so the proof is given on page 153. I'll let you read it there, okay? I'm going to go on to the next theorem, because the proof, as much as I am tempted to go through that proof in class, I really shouldn't, because that's not really it's true. We can give the proof here, fine, but you should see that again in real analysis, because this is a major result of real analysis, and this theorem is true over metric spaces, all right? In contrast, the theorem I'm about to share with you is genuinely complex. 10.3.9. You talked about metric spaces in real. Stop your snickering. You what? You did not talk about metric spaces in reals?
I think we briefly touched on this.
We talked about the
Okay. I reset. I'm reset. Let gamma be a piecewise smooth curve. All right? And fj uniformly convergent sequence of functions with fj going to f on E. Oh, not on E, but on gamma. What would that mean? I mean, what would we mean uniform convergence on a curve? Actually, my definition that I've already stated covers this, right? All I said was E was a subset of the complex numbers. It could have been what? I mean, it could have been anything, right? So our definition of uniform convergence already anticipates E being all manner of stuff. Then here's the punchline. The integral over gamma of fj of z dz, all right, converges to the integral over gamma of f of z dz. So not to belabor the point too much, but the reason I'm not going through that proof of the other theorem is really that the technique used in that proof is not a complex technique. It's just a standard trick of real analysis, and it doesn't really have much to do with anything else we're doing. That's why I'm not doing it. Okay, so here, that's the theorem. So here's the proof. We'll use the worst case estimator idea, right? So there's a worst case estimator for there exists epsilon j, right, on gamma such that what? Such that the difference of f of z, fj of z, right, and f of z is at most what? Epsilon j, right? Now, that epsilon j is, yeah, is the epsilon j, is that a function of z? It's not, right? I mean, at least we can choose one that's not, because we could use the supremum, which does, like the supremum looks over all points in gamma. So at the end of taking the supremum, we shouldn't have a point dependence. Like it shouldn't depend on the point in E. It should just be depending on j at most. All right, anyway, so there's that, the worst case estimator. And this is for all what? And this notation I haven't talked much about in here yet, guys, but so the default is that gamma is a parameterization of the path, right? If we put a bracket around listen to me, around gamma, that is the so-called trace of the curve, which I would sometimes just call the curve. So the bracket gamma is the set of points in the complex plane. Like this is literally a subset of C. Technically speaking, gamma, it's something like, you know, from an interval, which is a subset of the real numbers, to C. It's a parameterization, all right?
So you could write gamma in brackets equal to gamma of Dom.
That is true. Gamma in brackets, gamma in brackets would be gamma of I, yeah, or gammy. Let's see here. Sorry, I'll stop being an idiot. Actually, that's not likely to happen anytime soon. Now, this gamma, let L equal to the integral over gamma of dz. In other words, let L be the arc length. If L is the arc length of the path, then we can apply the in this case, ML theorem. And what's that say? It says that the modulus over the integral of gamma of fj of z minus f of z, excuse me, I'll get it eventually here. The integral of this difference, dz, right? The modulus of that integral is what? It's less than or equal to a bound for the integrand. What's a bound for the integrand? Though a bound for the integrand is exactly the worst case estimator here. So this is less than or equal to epsilon sub j, and then times the length, which is the arc length of the integral, arc length of the path over which we're integrating. And what happens as j goes to infinity? So as j goes to infinity, epsilon sub j goes to 0. L is fixed. It's the length of the curve. So this goes to 0 as j goes to infinity, and that suffices to show, right? Thus, the integral fj of z dz over the path gamma goes to the integral over gamma of f of z dz, right? As j goes to infinity.
So this is using integral properties and the assumption that the integral of f of j always exists.
Yes, there is a good question, Sam. There is a theorem that a continuous complex function has a integral. Good point. I have not stated that theorem, but that is true. Because I have not yet assumed that these are, like, if they were holomorphic, then we know more, right? But yeah, there is a theorem that says that each one of the sequences in the theorem is itself integrable. And this is saying not only is the limit function integrable, which is not surprising because it's also continuous by the previous theorem, and so we can write this result in a little bit different way. We can say that the limit as j goes to infinity of the integral of gamma over gamma of fj of z dz, right, is equal to the integral over gamma of the limit as j goes to infinity of fj of z dz. So uniform convergence of a sequence of functions allows us to commute the limiting process with the integration process. We've also seen that it allows us to commute the limit, the sequential limit, with the continuous limit in the complex case, right? This uniformity allows us to commute different analytical processes. Yeah. Sometimes. Okay. So that brings us to our next definition. Which is if we have a series, say sum j equals 0 to infinity of fj, is, this is a, I said sequence in the modes. This is a series of complex valued functions. All right? On E, which is a subset of C. Now, my question for you is, how do we define that? A few different things. First of all, the series converges to F on E if and only if what? The limit as n goes to infinity of the sum j equals 0 to n of fj of z is equal to f of z for each z and e. So what I just wrote is that the sequence of partial sums converges to the value of the function, right, at each point. This is pointwise convergence, which would just be ordinary convergence of the series. The series converges to the function f if this condition is met on E. What would we mean if we said the series was uniformly convergent? converges uniformly to F if this sequence, right, well, let's erase the Z here for a second. If this converges uniformly, right? In other words, the series is uniformly convergent if its sequence of partial sums is uniformly convergent. And as a general rule of thumb, anytime we define something for sequences, we've also defined it for series, where we insist that for the series, whatever thing we're talking about has to be true for the sequence of partial sums, right? This is the name of the game. So we can also talk about uniform convergence of a series of complex valued functions. All right. And this brings us to theorem 10.3.1. The Weierstrauss M-Test. Here it is. Suppose you have m sub k is greater than or equal to 0, and the series, which is, by the way, a real series, right? M sub k converges. So we have this non-negative real terms of which the series for which converges. And if gk are c-valued functions on E, which is a subset of the complex numbers, all right, such that the absolute value of gk of z is less than or equal to m sub k, all right, for all z and k, and e rather, then the series, the function series, sum over gk, converges uniformly on E. Ooh, this is nice. This theorem, this is a nice theorem, because to directly check uniform convergence of a function, it's kind of a drag, as we've seen at the start of today, right? If you can find a real series, a la calculus 2, which is bounding your function series above over the domain, right? And if that series converges, the real series converges, then we get uniform convergence of the series of functions. That is really much better than trying to find a universal best, to actually calculate the best case estimator or whatever directly, right? This is nice. It's a very nice result. This m sub j is called a, this m sub k is called a majorant for G. Converges to 0. No, well, that's, that would be necessary but not sufficient. It's not convergence of G we're after, it's the convergence of the series formed by G we're after.
Right, but
Series.
because you said some m sub k converges, does that mean that you can converge to any or converges to 0? On the first line.
Well, the series does not have to converge to 0, certainly not.
Oh, sorry.
It's okay. Oh, where was I? So here's the proof. Let's let Z be an E. And suppose we've got a majorant. so that the modulus of gk of z is less than or equal to mk. All right, for all z in E. Notice that the series for the absolute value of the function series pointwise, right, is less than or equal to the, and I'm being deliberately vague about where the sum starts because it doesn't really matter. It could start at 0, it could start at 1, it could start at 30. The starting point is not what matters, all right? So let's just not even write it. So the series of the absolute, see, this is by comparison, right? The comparison theorem which we have. So that would give me pointwise convergence, right? That much. Moreover, I say as absolute convergence implies convergence, we have that. So this gives us, this implies absolute convergence of this one, right? Hence, convergence. In other words, the sum over gk of z goes to g of z for all z and e, yeah? Because remember, we proved that absolute convergence implies convergence last time. So we have that there is a limit function, right? And now we need to argue that limit function is convergently, the limit is uniform. All right, so let's collect my thoughts here. So again, the sum, let's see here, gk of z is equal to g of z. All right. And maybe also is a better word to start with. Also, we have that the modulus of g of z is less than or equal to the sum over gk of z, which is less than or equal to the sum over mk. All right, finally, if we look at the difference of g of z minus the sum k, curses, fine. I guess my sum is starting at 0. K equals 0 to n, gk of z, which is equal to the sum k equals n plus 1 gk of z to infinity, of course. So here's the logic, guys. This is less than this, right? By the triangle inequality, yeah? And then that is less than, I mean, this is less than what? And what are we looking at? What are we looking at here? Where'd the n come from?
Yeah, what does that mean?
Oh, I'm an idiot. Duh. n is what I wanted to look at. That would make much more sense, because then we'd be looking at the difference between our limit function and the nth term in the sequence of partial sums, right? So by this set of inequalities, the difference between the limit function and the nth term in the sequence of partial sums is this. What is this? This is the tail. This is the tail of the convergent M sub k series. What happens to the tail of a convergent series as the starting point to the tail goes to infinity? This has to go to, this goes to 0 as n goes to infinity. So what you're looking at, guys, is the tail of the majorant series is serving as the best, as a worst case estimator for the limit function versus the sequence of partial sums. In other words, this shows that the sequence of partial sums converges uniformly to G, which is the claim of the theorem. So that does it. All right. Make sure we wrap up this section today. So I'm going to go to the projector at this point. We're almost done. We have 2 more results in this section. Next time I'll start on power series. That's my plan at the moment. So. But this, this result right here, this Weierstrass M-test, this is something that you need to like make sure you know and think about using. There are places we'll need to use it, I think. I guess it kind of depends on the direction I go, but let's see here. While I'm finding my notes, fun fact for you, the Weierstrass M-test still makes sense in A calculus. You can study uniform convergence and all this stuff for series built over an algebra, and this survives. Even despite the submultiplicity of the norm, there is still a Weierstrass M-test there as well. Not everything survives from series and sequences to the A calculus, but that's one of the things it does.
So in this proof, are we saying that M sub k is not epsilon? Or this partial, this tail of the M series?
Yeah, I'm saying this is serving as a worst case estimator. It's bounding.
So the trick, the deal is that the thing on the right here is not dependent on Z anymore.
Yeah. Indeed, there is no Z dependence on the tail of the majorant series. That is true. Now, I have a couple of examples that I'll show you here. One, if you look at the geometric series, we can look at the, what's a majorant for the, it's just funny. I think that's it. A tail, whoa, now I'm dizzy. I derived that last class, or almost derived it. And, what to say? What's my point here? Oh, my point is that when we look at that, that's the supremum of this is unbounded, which means that the geometric series does not converge uniformly on the disk. However, if you look at any subdisk, right, any r less than 1, even r equal to 0.999999999, we could be here till next week, that subdisk, it does uniformly converge on. So it's a funny thing, but you know, if r is less than 1, then this converges to that, which means it provides a majorant for the geometric series. So we do have uniform convergence of the geometric series on any subdisk of the unit disk, just not the whole unit disk. Here's a little bit more concrete example. If we have z to the k over k cubed, and if you consider the unit disk, obviously we have the inequality this is less than that. So 1 over k cubed serves as m sub k. And by the p equals 3 series test from calculus 2, you know that this converges. Consequently, this guy converges uniformly on the unit disk. This is why you need to know the Weierstrauss M-test, because these are nice test questions, right? If nothing else. Because all we care about is the test. And I'm just kidding. That's not you guys. I don't know why I'm putting you in that box. I'll take you out of the box. Let me put you out of the box. Next theorem, if we have a sequence of holomorphic functions on a domain D that converge uniformly, then their limit function is holomorphic. Ooh. That sounds more complex. And the proof goes like this. We'll use Morera's theorem. We need continuity to apply Morera's theorem, but holomorphic implies convergent, and the uniformly convergent limit of a continuous sequence of functions is itself continuous. So that gives us continuity of the limit function. Then if we take a rectangle with sides parallel to the coordinate axis, then uniform convergence of the sequence and theorem 10.39, which is the limit flipping theorem, says that the limit as j goes to infinity of the sequence is the integral of the limit, but this is this continuous function, and let's see here. But on the other hand, for each j, we have holomorphic, right? So any j, for every j, this is identically 0, because the integral of a holomorphic function around a rectangle is 0. So this is the 0 sequence, which is obviously 0. On the other hand, we've just shown that 0 is equal to the integral of the limit function around an arbitrary rectangle, which then by Morera's theorem says that it's holomorphic. Because Morera's theorem says that if you can show that the integral of a complex function around arbitrary rectangles parallel to the coordinate axis are 0, that serves to show that the function is holomorphic on such a domain. Yay. So there it is. Let me just recap that again. The limit of a sequence of holomorphic functions is a holomorphic function. What word did I forget? The uniformly convergent limit function of a sequence of functions is, if the sequence is holomorphic, the limit function is holomorphic. But the convergence, again, must be uniform. This also is true if we have a holomorphic function and we have that it converges uniformly on some disk centered at z0, radius r, then for each r smaller than r, and for each m greater than 1, the sequence of mth derivatives converges uniformly to the mth derivative of the limit function for each such z. This is very nice. This theorem is precious and strange to complex analysis. Let's go through the proof of it. So because this is uniform, we can find a worst case estimator. All right. And if we fix S that's between R and R, we can apply the Cauchy integral formula for the mth derivative. And that says that this mth derivative minus that mth derivative is m factorial over 2 pi I, the integral over this circle of this difference, right? But we can also write this, all right, I got to do this next time. We must go over this in class. I should not gloss through this. This is important. What it's going to tell us is simply this. All right, so the thing that maybe you don't appreciate as much as you would if you had real analysis already, but if we have a uniformly convergent real sequence of real functions, each of which is differentiable, all right, they can converge to a function which is not differentiable. So differentiability is not preserved even under uniform limits in the real case. This theorem, what it's saying is that if we have a uniformly convergent sequence of complex functions, that the limit function is not only is it complex differentiable, but the second, the third, the fourth, the fifth, however many derivatives you like of the complex, of the limit function exist and serve as the limit for the corresponding derivatives of the sequence term by term. This is really, really a very nice result. It takes additional technical conditions to make this happen for real functions. But here, it's something we can prove in 10 minutes that I don't have. So I'll start next class with that, and that will naturally lead us to power series. All right? Thanks, guys. I shut up.